going to show us what, why, and how to hack. We have core developer here to keep him honest or upset. And Richard has got to behave himself. You know the code of conduct. Anyway, let's give Ryan a warm welcome.
Howdy. So yeah, this is me. In real life, I'm quite a serious software engineer, but in my spare time and on stage, I like to muck around with fun stuff and make Python do fun things. So this is a little bit of a rambling talk about Python and some of the stuff that it does internally. So it's not all just about how to do wacky stuff. I hope to show you a little bit about some of the internal details of Python that you never really see during your day-to-day interactions with the language, but that are quite interesting, and the details of which do have an effect on you and on your programs. At the end of this talk, I'm about to advise you to not do a variety of things that I show you in this talk, but my hope is that having seen some stuff under the covers and how it works, it will make you a better Python programmer, just because of because of having a different perspective on things. So Python is known as an interpreted language, like they say it's a scripting language and so forth, but really it is both a compiled language and an interpreted language, right? You've all seen these PyC files. You start out with your source in hello.py that gets compiled by Python and cached as this hello.pyc file, and then that compiled code gets interpreted by the Python executable and it prints out hello world. So we have both an interpreter and a compiler, and in the source they actually live in quite distinct places. They're quite distinct bits of code, and I'm interested in the stuff that exists in the middle. So the bytecode format that lets these two halves of Python talk to each other. It's worth a brief mention about why Python is structured this way. I mean, you'll certainly find interpreted languages that don't have a bytecode format. They just parse their source directly into an AST, and then the interpreter walks that directly and executes the code. But having that split allows you to do some interesting things towards both efficiency, so you can have the core of your interpreter not deal with a lot of silly cases in your syntax, deal with a more uniform and a simpler representation. And also in terms of simplicity of implementation, to keep those concerns separate. Importantly, of course, all the cool kids are doing it, right? The JVM has a bytecode format and .NET has a bytecode format. It's quite a well understood way of structuring an interpreter. There we go. So if I were to say to you, look, what is the most basic unit of code in Python? A fair enough answer would be, well, it's a function, right? I def a function, it's got some code in it, and I can execute that code. Not quite. Python actually has these things called code objects. They live under the covers of all of the things that you do in Python. And when you define a function, you're actually declaring two things. You're creating a code object, and you're giving it a context in which it's supposed to execute. So, yep, I'm going to pop over here and have a little bit of a chat about that. So this is my delightful, not at all scripted Python shell. And if I define a function like this, right, then I can call it and it says the message and so forth. But if we have a look at the attributes of this function object, you see it's got lots of interesting and enticing things with double underscores, such as closure and code and defaults. The one that I'm interested in is this double underscore code object, which, as it says, is a code object. And it has this double underscore globals, right? Which, if you have a look at the keys in this dictionary, actually corresponds to the context that I'm currently executing right now. And in fact, to a first approximation, calling this function basically entails executing that code object in the associated context of that function, right? It does the same thing. If I take that code object in isolation and execute it in some other unrelated context, bad things can happen, because that code object is expecting to find a global variable named message, which has gone missing. I'm executing it in a different way where that function wasn't defined, so it's not finding the things that it expects. What have I got here? Yep, so code objects, they have a lot of interesting attributes on them. This binary looking string here is the bytecode that the Python interpreter looks at and interprets and decides what to do. This, for example, is a list of all of the names that are referenced in this bytecode. And part of the reason why that's such an unintelligible string is that it contains various indirections and pointers out to say, well, load, the thing that's got the name, that's the first name in CO names, and various levels of indirection. Here's all of the constants that the code object uses, and now I need to go back to the slides. So these objects, they represent compiled Python code. They're raw instructions for the interpreter, their names, constants, metadata about that code that you defined. And they're actually one of the really core primitive types in Python, right? And they're immutable, which we'll get back to in a minute. You never really see them unless you go looking for them, but they're quite central to everything that Python does, and they show up in a lot of different places. Here's an example. .pyc files. You all seen them? Kind of vaguely what they're for? Yeah, okay, good. So these are basically caches of your compiled bytecode that Python generates so that it doesn't have to parse your code over and over again. What you may not know is that they're a really very simple file on the inside. And there's three things, right? The first 4 bytes are a magic number, which basically stops you from running a pyc file from Python 2 on Python 3, or something like that. The next 4 bytes are a timestamp, so that you can tell if your cache is out of date. And the rest of the file is just the code object that I showed you before, dumped out in a binary format. Where did my presentation go? Yeah, thanks, OpenOffice. Let's try that again. Where is my... Where's Go? Here we go.
Oh my god.
Yeah. Dun, 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 dun. Yeah, I hardly ever use that one. Okay, so... Oh, God. Anyway, you can see that, can't you? If I grab the OS module, for example, and I have a look at the file that's been loaded from, obviously that's loading from a cached bytecode file, right? If I read the contents of that file in, I can check, here are the first 4 bytes. That's a magic number that Python knows about internally. This is a 32-bit timestamp encoded in some endianness that I don't recall off the top of my head. And the remaining 26,000 bytes of this file, I can do this to. Do you know about Marshall? Yes. If you don't know about Marshall, do you know about pickle? Yes. So Marshall is basically a really fast pickle that only works with core Python data types like integers, tuples, and funnily enough, code objects. So the entire body of that file is just, imagine taking a code object and dumping it out as JSON. It's a similar sort of idea. And in fact, if I create some new namespace and and I just load that straight out of the file and execute it in this empty namespace, I will in fact get something that looks an awful lot like the built-in OS module. And I could grab functions out of there and use them as if I'd just grabbed them off OS itself. So code objects are everywhere. There's this nifty little module called dis, which stands for disassembler, and it lets you have a peek at what's inside your code object. So here's a silly little, very quickly typed out function. This is a very friendlier, a friendlier version of that little binary string that I showed you before. And I'm about to do a couple of slides that explain what all of this is, but basically this is a series of instructions corresponding to the code for that function, right? We load hello world as a constant, we print it, and then all functions return something, right? And if you don't return something, you return none. So we load none and return none. And I think, oh no, here's a more complicated example. Good. So, oh my God, did I get that right? So this is a little loop, and if you've done any assembly programming or something like this, the ideas here will look pretty familiar, right? We set up our variable x, and then there's a bunch of stuff here about getItr, forItr, and so forth. And at the end of the loop, there's a jump back to position 19. So these high-level control flow constructs compile down to very low-level things like jumps and tests and this sort of thing. So I've got a little bit more palaver about that on the actual slides. Good. So the Python interpreter is quite a classic stack machine-based VM, right? You've got this array of instructions, which I just showed you a printout of. You've got a pointer to where the next instruction is, and you've got a big stack of objects that you push and pop things off of. It's got a variety of different opcodes, some of which you saw there for manipulating the stack, right? So you've got instructions to say load some value onto the stack. And it could be a constant, you could be loading it from your global namespace, you could be loading an attribute off an item. You can manipulate the stack in various ways. You've got various ways to jump to different parts of the bytecode, and this is basically what you use for an if statement or something like that. Jump to another instruction if the top of stack is true. And then there's this whole host of individual opcodes dedicated to the primitive operations in Python. So you say, x plus y, that gets compiled to a binary add. You say call this function, that gets compiled to a call function. So they're very high level opcodes that correspond quite directly to the things that you do in a Python program. A lot of them. So this is Hello World, done step by step from the point of view of the Python interpreter. You've got that string of opcodes printed out very friendly-like, and they reference various objects that live in the interpreter's namespace. And it just says, look, load, no it doesn't, load the constant hello world, that gets pushed onto the stack, print that out so it gets popped off again, it prints out a new line, it loads the return value, pops it back off again. And more complicated functions get a lot more complicated, but that's the basic idea. To the source. So you can imagine that sort of, seriously, this is a checkout of CPython trunk. You can imagine that sort of a structure, it would be quite easy to write a dumb little interpreter for that, right? You need a pointer to the current opcode, you need a pointer to the top of stack, and you need a big switch statement around all of the opcodes to say, if I hit pop type, I do this, So this is execute compiled code. I love that, to do, speed up this and that, and whatnot. And remember where to jump to for this. This is the function deep down in the middle of Python that executes your code, right? And you can see it's got a variable for the current opcode. It's got a variable for the top of the stack, and it's got various temporary variables it can use. It's got a whole lot of stuff about making things go fast, which are really interesting, but I'm not going to do it here. But down here in the guts of this function, there really is just a big switch on the opcode, which by virtue of these macros gets compiled into something a lot fancier. But it is, if the next opcode is this, do this. If it's a load fast, do this. So the core of that very simple interpreter structure is still very much there in the source, and I think that's a great feature of CPython, that the ideas inside that interpreter are very approachable. Now, do you need to know this stuff? Probably not. You will quite happily be a very productive Python programmer without ever seeing the words code object printed into your screen. But I believe that understanding it will make you a better programmer because it helps you to understand why various things happen. And I'm going back over here to do a little timing demo. I'm going to define two really stupid functions that don't do anything but spin for a while. One of them uses this while one constructor, right? And the other one is exactly the same, except it has while true. Now, question. Which one of... Yeah, I know, I'm about to bring that up. This is Python 2. Which of these functions do you think will run faster? The top one, correct. So if I grab time it, and stop, there we go. That runs pretty quick. If I run while true, that is appreciably slower. Right? That's not just noise, that is appreciably slower. The key to what's going on here is in the bytecode. So if I have a look at what's going on inside while true, have a look at line 3, where we're setting up our loop. The very first thing we do is load the global variable named true, and if that happens to be false, we jump out of the loop, okay? Which seems silly, and Python isn't really that silly. If I have a look inside while 1 at setup loop, that's gone. It doesn't say load 1, and if 1 is false, jump to the end of the loop, right? The reason that while true is slower than while 1 is in case some idiot like me comes along and does this in the middle of your code, and that will terminate straight away. In Python 3, they made the very good step of making true and false keywords, so you can't do this anymore, and both of those will run equivalently fast in Python 3. Good. How am I going for time, Mark? Good. So, okay, this is, now that we know about all of this, let's have some fun. If you want to play around with Python's bytecode format, here is a piece of advice. Install byteplay. This is the very first thing that you want to do, because code objects in and of themselves, they're designed to be executed. They're designed to be executed efficiently. They are not designed to be tampered around with and poked around with. If you go into your REPL and type help types.codetype, you will be greeted with the following message. Create a code object, not for the faint of heart. Which should be a pretty good warning sign that you're not meant to tread here. And in fact, look at all of these crazy things that you have to supply to the constructor of the code object. Line number table, exactly. Some of these things include a count of the positional arguments, including arguments that have default values. A tuple containing the names of local variables referenced by nested functions. The required stack size, including local variables, which requires you to know the stack effects of all of the opcodes in your bytecode. A string encoding the mapping from bytecode objects to line numbers. For details, see the source of the interpreter. Byteplay hides all of these details. It gets them right, or right enough that you can, be productive with it. So yeah, you want it. Let's pop back over here and have some fun. So here we go. From byteplay import star, and here is a simple little hello world. All right, it does its thing. It prints out hello. Let's make it do something else. Let me just move that over a little bit. Byteplay has this object called code, all right? And you can instantiate a byteplay code object from a Python level code object, right? We get C is now a code object that we can play around with. Here it is, byteplay.code, and here is the corresponding set of bytecodes. So this is what you saw before for hello world, right? Load const hello world. It's a list of tuples of opcodes and their arguments. So for example, print doesn't have an argument, so it gets none. Load const has an argument, so we give it hello world. If I go in here and just say, look, instead of that load const hello world, let's load a different constant. We'll turn this byteplay level code object back into a Python level code object. And this is a fun thing about functions, is that they're quite happy for you to just replace their code object out from under them. And then, when we run that function, it's going to run our new bytecode and print out something totally different. So what I want to do, and I believe, good. What I want to do is fix up while true for you at the moment, okay? So we're going to define a little decorator which gets, which basically says, let's not be stupid. People aren't going to change the values of our built-ins out from under us. And if I get a function, I can apply this decorator to it. I'm going to rip its bytecode out into something I can play with, and I am going to walk over all of the bytecodes in that function. So just go through that list one at a time. If I come across something that is a load global statement, and that happens to be something that is in the set of Python built-ins, then I'm going to replace that with a direct load of that value. All right, just load it straight away. Pop that code back on there. And that works as a nice little decorator. So this is what while true used to look like. I can apply this little trick, and we have an improvement. Right? We've eliminated this constant looking up of the name true in the global context. But that's still slower than while one used to be. And if you have a look at the bytecode, we're now doing something a little bit stupider, because we're loading a constant true and checking to see if it's false and jumping out if it's not. So what we really need to do is get rid of this dead jump. Okay, remove dead jumps. Same deal again, we're going to grab that code and have a look at it, and this time we're going to iterate over pairs of consecutive opcodes. So if the opcode at position I is a load const of something true, and the opcode at position I plus 1 happens to be pop jump if false, we're just going to delete them, because that will never get executed. Okay, and obviously in the real world you could have a lot more cases here. Pop jump if true springs to mind. That's it. Return the function. How many people write decorators and forget to return the function? Yeah. Took me a few tries to get this right. Yep. And if we apply timer again, we're now getting essentially the same result that we would got if Python could apply these optimizations natively. So that's the sort of fun you can have with this sort of thing. And you can see that we've now got rid of all of that unnecessary testing and loading at the start of the function. Okay, back to the slides. So that's a taste of some of the fun stuff you can do. Don't do this to me. Oh, good, excellent. So I have a bunch of projects that kind of try and take this and do fun things with it. One of them is called Promise, which is basically those optimizations I showed you writ large. So this is basically that. You say, this name keeps getting looked up. Look, I promise you that the built-ins are constant. Fine. Make the necessary adjustments to my code to make it run faster in the context of this promise. And that will make the replacements that I just showed you and optimize that code to be only looked at once. With hacks I did at PyCon last year, and it's still one of my favorites because you can do all sorts of wacky stuff that makes people, think twice about what they know about Python. So this is a namespace hack. And if I have an object, right, I can do this little declaration. I can say, using this object as a namespace, execute the following code. And that X and Y won't actually appear in your local variables. They will then appear as attributes on this object. So it's intercepted the bytecode and rewritten it to set the attributes instead of set local variables. And there's a whole nother level of evil behind that, which I could get into if we have time. I did an add-in line last year as well, and this is basically the idea that, look, function calls are expensive, so this function was going to be called a bunch of times in a loop. Wouldn't it be great if I could, like in C, mark your functions as inline and just say this function gets called a lot. It's probably worth putting the code directly inside, where it's going to be executed. And you can construct this little decorator that does the necessary magic to pull out the function call bytecode and replace it with the bytecode of the function itself. There's lots of fun corner cases to be had in there. What I really came here to say is actually, no, that's probably not the best idea. I love to muck around with this stuff, and I think it really helps understanding your tools. It will make you a better Python programmer, but I've never deployed a bytecode hack into production code, ever. I've deployed a few frame hacks into production code, but so has the Python interpreter. So look at the source for named tuple sometime. So yeah, seriously, this is fun to play with, but probably not the best idea. It'll work in production, but you're setting yourself up for a maintenance nightmare, so for learning purposes only. Yeah, thank you very much. I love to talk about this stuff. If you're interested in some of the projects using this, they're on my GitHub. This is the module for looking at bytecode, and it's got documentation of what all the bytecodes are. And yeah, if you're interested in having as friendly a live coding experience as I had in this talk, play a piano and use it for all of your presentations. Because it's basically a little fake Python shell that you can type into and play stuff out. So yeah, thank you very kindly. No, someone else.
I'll be nice. Well, nice to you, but probably not nice to Nick. So given that we have super in Python, which is, its own kind of evil, why can't we have namespace in Python?
Why can't we?
Yeah.
Well, we can. You can help me with the pep. How much time have we got, Mark? 5 minutes.
That's long enough to write a pep.
No, I was going to show you this other thing, but maybe I'll just prep that while people ask questions.
Oh, there's one way out the back there.
That's the microphone.
Yep.
I was just wondering, the bytecode in Python, that's not part of the official specification of the language, is that correct?
Correct.
Yeah, because other VMs obviously.
I believe that PyPy uses a similar format, but they have some of thec own opcodes and stuff, and it's not even guaranteed not to change in backwards incompatible ways between different versions of the interpreter, which is why your PyC files have that magic number. Sorry? We don't even guarantee the AST. Exactly. So yeah, as Nick says, there's new stuff with the AST that you can muck around at a slightly higher level as well, but again, that's not guaranteed.
As part of that, does that mean that the dist module essentially can print anything? Because when the bytecode changes, its output could be completely different. Is that? I
mean, it's gonna usually not.
Yeah.
But yeah, you probably don't want to. We were just having a conversation about this with Nick. You probably don't want to depend on the output of the dist module for anything except learning purposes. Yeah, don't do that. Don't do that.
Okay.
Yeah.
So is this how the Psycho module works?
Lord, I hope not. No. Psycho is a very different beast. I mean, that generates assembly, right? An x86 assembly all the way down. But I imagine that it starts from where I've got to here with the bytecodes, and then, you know, does a whole another level to turn that into assembly deep down. But yeah, I've never peeked beneath the covers of Psycho. Maybe one day.
Anybody else?
Since you brought up Super, Richard. Yeah, no, well, look, you can actually get the awesome zero-argument Super from Python 3 instead of this awful, redundant, repeating yourself stuff in Python 2. A lot of people think that you can get away with doing this, like just look up the class object on the object itself. That's very, very wrong. Self doesn't have enough information to figure out how it should call Super properly. And Byte doesn't have enough information. What I mean is, doesn't provide enough information in the friendly public API. What you can do is reach back into the calling frame, figure out what the name of the first variable is, and then read it from the frame's local variables to get self, and then walk the MRO of the object that you just found to see which of the classes along that MRO contains the code object that you're currently executing, which is the class that function was defined in. And then you just call super normally, or panic and raise a runtime error. So that much code will get you zero argument super in Python 2 if you dare. And while you're in there, you might as well grab the name of the method that you're executing, and then you don't even have to write super at all. You just say, call my super method with the following arguments. But yeah, you probably don't want to go there. Thank you. That was going to be a lightning talk, but the slots filled up too quickly, so.
Just a word of warning, this is your last chance to get coffee.
Oh.
Hugh on it.
Last chance to get coffee. At this conference for free.
Okay, if we don't have any more questions, let's give Ryan show our appreciation.
Thanks. I'm probably not still on. Can I have that one?